tranne lo usiamo per andare a fare. Sì, è vero che devi stare chiuso che c'è il microfono ambientale, quindi puoi utilizzare questo. No.
Ma io preferirei, cioè in genere riesco a muovere un po', però se non c'è.
Ma quello di prendersi uno si muove qui a questa distanza.
Sì, questo prende
prende comunque tutto imbarazzante.
Però per switchare.
Sì. Vabbè, però ti muovi. Se ti vuoi muovere devi tornare lì.
questo è il sesto, no? O il quinto?
Sì, mi sembra. Sì, ho quinto sesto, perché è iniziato a.
Scusa, il 2 dicembre? Sì. Sì, è il
Sì, il
sesto.
sesto.
Sono qua.
Stai qua tutta la mezz'ora?
Metto nel
Ma no, vedi qui adesso controllare questo posto. Sì, no, ma stai lì, ora aspetto. Sì. E dopo ci diamo il cambio che si va più lì.
Okay, guys. Silence, please. Okay, today we have the sixth seminar of the series. We have two presentations. The first is by Simone Formentin. This is associate professor here in the section of automation control. The second one is by Federico Lettu. Okay, he's here. And you can start. Thank you.
Thank you very much. Thanks to all of you for attending. So I'm quite glad to talk about this topic today, not only because it has been my, let's say, favorite research topic since the beginning of my PhD, but also because I think that this is has a great potential in systems and control. So the use of learning tools to automate the design of controllers is really something that is not just modern and interesting from a scientific point of view, but it's also very useful in many applications as we will discuss. So first of all, since some of you do not come from the same field, so why feedback control? Well, actually because feedback control is everywhere. And it's not hard to believe that whatever application you think, let's say technological application you think of today, starting from safe collaborative robotics until autonomous driving or vehicle dynamics control, biomedical applications, control of tokamak plasmas, everything contains one or more feedback loops that are dedicated to the control and let's say the decision making, the automatic decision making for critical decisions, let's say critical steps and tasks. And the common line behind it is the hidden technology, so it's the controls actually. And you can see it in the hidden scheme behind the pictures, where the common line, so the common feature behind all of these applications is the fact that in all of these systems you have a plant, so something that you would like to control, that you characterize in terms of a series of output variables, so a number of variables that you measure, and you assume that you can act on the plant, so you can you have a series of actuators that allow you to interact with the system and change its behavior in order to make it behave as you prefer. And the reference behavior is expressed in terms of a reference, a series of reference values for your outputs. So the way that control algorithm works is just to take the measurements of the output, compare them with the reference behavior, and then take a decision depending on this error between the desired behavior and the measured one. And this is also very common in many other applications, of course, not just the four of them. And you can see a brief list there. You can see flexible manufacturing, floating structuring, offshore engineering, and many others. What is the traditional approach to control design? So how can I devise a control algorithm that takes the measurement out of the system and interact with the system in order to make it behave according to the specifications of the user? Well, if you take a simplified feedback loop, like the one depicted in the slide, where you just have a set of inputs U and a set of outputs Y that characterize the plant, and a controller that embeds also the sensing technologies and the actuators, well, the traditional approach is called model-based design. So it's not hard to believe that in order to understand what is the best action to take on the system, you need to know how this will translate into some output behavior. Okay, so you need to know G in order to decide what is the best U. And this means that you need a mathematical model of your system. And there are two main approaches to modeling. One is the so-called first principle model, or white box modeling, that is basically expert-based. So you know the physics of the system, you know the mechanics, the laws of electrical circuits, the chemical equations of the plant. You put all of them together, and the set of equations become your model, based on which you will design a controller. A second approach is called black box approach, or system identification, and it's another way, an alternative way to find a model of the system based on the correlation between input and output measurements taken from the plant. Okay, so this is closer to what machine learning does, but usually the main difference here is that G is typically a dynamical system, so it can be described by differential equations or difference equation. What is the problem with this traditional model-based design approach? Well, I would quote George Box here with an old sentence, but let's say still valid. All models are wrong, but some are useful. So if you take many modern applications, you see there some logistics, some network applications, social networks. It's very hard to find a model in all these situations that is both simple enough to be used for control, but also reliable and accurate enough to really represent the behavior of the system. And so this is why it has been estimated that 75% of the cost associated to a control project is usually devoted to modeling. Okay, so this is a real problem, a real issue. So we can actually tackle the problem from a different perspective and say, okay, let's follow what Vapnik suggested in 2006. So he said, when solving a problem of interest, we should not solve a more general problem as an intermediate step. What we do in model-based design is typically the case. So we try to optimize some fitting costs. So we have a bunch of data that we call the N, and we would like to find a model of the plant G that we call G hat, based on some maximization of a fitting measure. Okay, so we solve very complex problem because then we have to decide what is the structure of the model, what is the functional dependency between inputs and outputs. So it's a very complicated problem. And maybe this is only aimed to find a couple of control gain. Like in PI controls, you have just a proportional gain and the integral gain, and that's it. And so you solve a very complicated problem in order to optimize a couple of parameters. Okay, and the other problem is that when you do modeling, when you optimize your data and you transform it into some model, you optimize something that is not exactly oriented to control. So the model that is the best in terms of data fitting might not be the best in terms of control performance. And so the approach that we will discuss here in this presentation is how can we go direct? So how can we learn directly a control law starting from a bunch of data taken from the system? And this is not a new topic. I mean, there has been a lot of work, research work, both in the automation and control area and in computer science, starting from the 60s. So the first approaches were under the hat of the dual control techniques. So they studied the interaction between identification and control using normal operation data. Then there was the rise of adaptive control, and then the use of neural networks before, current technology was available. And then most of the researchers decided to develop techniques that were comparable with traditional system identification and that used only offline data. So you run an experiment of the system, you take that experiment, you design a controller, and then you implement and you deploy the controller directly there. And more recently, there have been some, let's say, efforts devoted to learning-based model predictive control, which is the, let's say, the current state-of-the-art technology in many complex applications. So the outline of the presentation is a very subjective view of the area. Is just, let's say, an overview of what exists in this direct approach to control design, starting from a bunch of data, towards more advanced controls. So I will summarize basically what are the main key ideas to skip this modeling step, so to avoid to do this complicated task before going to the control design, and then I will close with some, let's say, open challenges. So but let's start with the key ideas to skip the modeling step. I will say there are many contributions in this field, so you can list hundreds of papers in direct data-driven control, but I would say that you can basically collect most of them, and according to my opinion, you can basically collect all of them in 3 macro groups. So there are 3 main ideas that allow you to really skip this modeling step. The first one is the use of gradient descent. And this is one example of how you can do it. So what I mean, consider this feedback loop, and you assume that you have a controller that's already implemented in your loop. So you have C theta with a certain instance of theta. And what you want to do is to improve the quality of this controller in order to better match the desired specification. So one idea that you can actually follow is just to use gradient descent by saying, okay, if I update the controller parameters by going towards the direction of the negative gradient, of course I will improve my performance. The only thing that I need to know is the gradient of the cost function. That could be the one indicated in the slides, for example, the mismatch between the reference and the output, or the squared mismatch, and I have to compute it from the data, okay? And that's basically the key issue, because if you write the expression of this gradient, you can see that, okay, this is basically the sum of the differences between reference and output, but also you have the derivative of y with respect to the controller parameters. And you don't know how y change if you change 1 or 2 gains of the controllers, of course. You can also show it easily by, if you write down the expression of the system. I will use here a transfer function representation, so hoping that will not look too weird to some of you, but basically you can actually show that this derivative is a function of the plant model. So if you don't have the plant model, there's no way you can compute this derivative. And the key idea using gradient descent to skip the modeling step is to run new experiments. So you can actually show that if you run a second experiment by injecting in this way the previous tracking error, so the difference between R and the collected measurements of Y inside the input of the system in a new experiment as an additional input, you can show that the output of this new experiment will be exactly the gradient that you're looking for. And then, okay, this is just a detail. And this is basically a model-free way to compute that gradient that allow you to improve the quality of your controller experiment after experiment. Just a brief remark, this is in close connection with what model-free reinforcement learning does. And with model-free reinforcement learning, I refer to all those techniques that are really model-free, because there are many approaches in reinforcement learning that are denoted as model-free, but that actually require some model of the value function, for example. And in those cases, you still require a model, so we will not put these techniques under that hat, let's say. So I'm really referring to direct policy search methods, like, for example, reinforce. And if you look at these policies, you can notice that the update rule for theta, so the controller parameters, is very, very similar to what we have just seen in the previous approach. So you still have an update equation, and the update depends on some data-driven estimation of the gradient of the cost with respect to the controller parameters. This was one approach to skip the modeling step. A second approach is based on the fundamental lemma, and this is something that comes from a completely different field, which is the behavioral systems theory. So let's take a system that's still linear and time invariant like in the previous case, and it's written in state space form. So you have a bunch of difference equations that describe the system dynamics, and then you map the state onto the output through a set of algebraic equations. You assume that you have a data set available and that you can run an experiment on the system, so you can inject a certain input sequence such that this input sequence is persistently exciting. So it has some properties, some nice properties that will allow us to use this experiment in an informative way. And this persistency of excitation property is basically a rank property of this matrix made up with a sample of U. Well, we can show that actually any input-output trajectory of the system can be written as a linear combination of these observed trajectories. So once you have a set of trajectories, you can write any other trajectory as a linear combination of this. Okay, so you change the weight of this linear combination, you're changing the trajectory, but any trajectory can be expressed like this. And this is a good news because like this you can substitute the model information inside the matrices B and A in the model description with a database description. So inside those U01N and XD0N, they're just samples of state and input that you collected out of the system. And then you have basically a database description that you can use to do prediction, simulation, and also formulation of database formal constraint. This is not the end of this because actually this leads very easily to model predictive control formulations from the data. So suppose that you have a receding horizon formulation of your control problem. So you have an optimization problem where you have two different costs. For example, one is the tracking of the reference, and the second one just weights the aggressiveness of your input action. And then this must be optimized subject to the system dynamics and some constraints. For example, if the input saturates or you have some different constraints on the signals. Well, you can substitute the system dynamics with the previous equation, so the database equation that you have here, so that the whole formulation of the problem is data-driven, and you will find the best linear combination, so the best selection of G, so that the control problem is satisfied and is fulfilled. These are some nice properties like feasibility, satisfaction of constraints, exponential stability that I will not enter into the detail, but just to tell you that we have nice theoretical properties of this. There is a third way to skip the modeling step, that is whenever you have a reference model as a problem formulation. So suppose that your objective is to make your closed loop equal to some desired model that we call M. Okay, so M of Q is a transfer function between the reference and the output, and we would like our closed loop system to behave like that. So basically, if we write the equivalence in terms of transfer functions, we have that M must be equal to GC over 1 plus GC. Okay, this is a very basic equation that we encounter in courses on fundamentals of automatic control. Well, if this is the case, then we can define a certain ideal controller that we will call CID. And this CID has an expression that is clearly depending on the inverse of the real system dynamics. So looking at this, we could conclude that actually learning the ideal controller is at least as difficult as learning the inverse of G, with additional problems. For example, it's not causal, it might be non-minimum phase, you may have some fixed parameterization, so you have to do controller reduction after that. So it might not be, let's say, a good situation to tackle. However, if you consider the specific case where you have a model reference specification and you want to design a fixed order, fixed structure controller like a PID, like proportional integral derivative controller, which is the simplest class of controller you can think of, well, this becomes a valuable reformulation because we can directly map the data that we have, so a bunch of offline data, onto the set of gains of the controller. And how can we do it? Well, consider an optimization problem like this. So we would like to minimize the distance between the actual output and the desired output, R, okay? Or actually not R, but the output of the desired model. This must be done subject to the system dynamics and the controller dynamics, okay, that are the second and the third equation. So we have two problems. So first of all, the solution here depends on the choice of the reference signal, which should not be the case, at least in the linear setting. And the second thing is that it depends on the system dynamics, so the polynomials A and B that you see in the second constraint. Well, actually, we can get rid of this in two ways. So first of all, we can invert the second equation and say that the reference is actually a function of epsilon and y, which is the decision variable and the output, so we can remove the first constraint. And then we can also get rid of the system dynamics, because we can see that the only reason why we need the system dynamics there is to say that u and y must be correlated because they are the input and the output of a certain system. But if we substitute u and y with the data taken from the system u and y, these are in principle correlated because they are taken out of the system, and so we can get rid of the second constraint and substitute it with the data, with some, let's say, remarks, because of course when you substitute a constraint that is valid for any t with a bunch of data, you have to be careful that this is valid only for t that goes from 1 to n, and then the data might be noisy, so you have some problems, but at the end you have a model-free optimization problem. So what is the problem then? It seems that we have several ways to do model-free control, so without first identifying the system dynamics and then designing the controller. So why should we need to study this farther on? Well, the main reason is that most of the efforts, at least until 2010, have been devoted only to parametric control design, so just PIDs or similar controllers. And so there are many open problems, for example, nonlinear control systems, or when you want to select, let's say, any controller with a free structure, or when you want to derive formal guarantees. So when you want to say, okay, I have this nonlinear control, I want it to be I don't know, stabilizing for the whole system, or regionally stabilizing under some conditions, I don't know. So we can extend these ideas to LPV control, so we can basically replicate the same strategy that we encounter with in model-free control in the LPV setting. And LPV systems are basically linear system where the dynamics is linear between input and output, but it also depends on some exogenous signal that we call scheduling signal, so some scheduling variable. This is the case, for example, in many aerospace applications where you have, for example, the thrust and the speed of the airplane that are linearly correlated with each other, but then the dynamics depends on the altitude of the plane. Okay, in this case, the dynamics becomes more complicated because all the equations also depend on this scheduling signal, for example, the altitude of the plane, and these are also time varying because the altitude can be a signal that varies with the time. And this introduces an additional problem, because in the polynomials that we had previously, we have some functions of this scheduling signal that could be any function. So in principle, you could have even nonlinear dynamical function of these parameters, and so you need to learn these functions together with the parameters of the controller. Okay, suppose that you have a gain scheduled PID, so you have two gains of the controller, but these gains change with the scheduling signal. Then you need to understand what is the functional dependency of this scheduling. And the way we tackle this, we deal with this, is using traditional machine learning. So in this case, we use the Gaussian process regression, for example, and in this way we could guarantee that we find, let's say, accurate description of these functions with no overfitting, because the problem here is that you could easily overfit. This is a very easy example. So we have a DC motor with an unbalanced disk, and we control it with voltage. We want to control the angular position. The system dynamics, if you know it, is this. And if you want to solve this problem from a model-based perspective, this is rather easy, because you can see that you have a state matrix, which is a function of this term sinus of theta over theta. And if you take this as a scheduling parameter, this is a find in the scheduling parameter, which makes the computation of the controller rather easy in traditional LPV design. But in the data-driven setting, we don't know this, so we don't know the structural dependency on theta, and so the only thing we can say is that the system dynamics depends on theta, so the angular dependence, but we don't know how. And so we take the scheduling signal to, equal to theta itself. So it's a quasi-LPV because it's not an exogenous variable that makes the dynamics change, it's the state itself that changes the system dynamics. So we assign a certain design behavior. I will not go through the details of this. And we have certain controller parameters because we assume that the structure is fixed a priori with some integral action to have a zero steady state error. And this is the result. So quite satisfactory. You see in blue, you have the reference signal, and in dashed line, you see the output, the actual output. And you see that the accuracy is pretty good. It seems that even if the system was originally nonlinear, we track it very well. So we have sort of feedback linearized the system with a data-driven controller. Where is the trick? That I'm cheating here. And where I'm cheating? I'm cheating because I selected a reference model which is very easy to achieve. So it's very low demanding, so I'm asking my closed loop to behave quite well. I'm not asking anything special. And so my controller, even if it's not very complicated, can achieve this with no particular problem. If I had selected a different reference model, for example, with a very demanding bandwidth, or let's say very fast response, I would destabilize everything. Okay, so how can I solve this? So I don't know how to select the reference model properly because I don't know the system dynamics. So I don't know what to ask in closed loop if I don't know what I have in open loop. Okay, so we decided to tackle the problem from a different perspective. So suppose that you asked for a low demanding reference behavior for the loop. Then we can add a secondary loop that plays the role of a reference governor. So basically changes the reference to the inner loop. And this way we can actually do two different things. So first of all, we can boost the performance. So if we see that we can do more, we can boost the performance if we design that reference governor as an optimization-based controller. And secondly, we can also take into account the constraints that we might have on the signals, for example, some saturation of the input action. And why can I do it in a data-driven fashion? Well, actually, because the outer controller, so the reference governor, sees something that is completely known, because we know that we designed the internal controller in order to achieve a certain M in closed loop. So we know what's the model of the system, even if we don't know what's G. Okay, so we can design this scheme very easily. We have optimization of the output, optimization of the reference, constraints on the output, system dynamics. Everything is properly and suitably formulated, and this is the result. So you see that when I add the MPC, so the outer loop, I have an increase of performance, so I have a faster response, and I can do it with, let's say, without having problem with the, let's say, the computational constraints of the system itself, and I can also comply with the constraints. What is the trick? So the main trick and the key idea why it works is that the reference that you inject into the inner loop is the one that you see in red. So you basically boost the performance because you see that the system can do more, still complying with the constraints. And then when you're reaching the steady state, then the reference is driven down. You can do this for LPV systems. You can also do it in a switching setting. So if your system is switching between two different dynamics, so in a piecewise affine case, and the formulation is the same. So the only difference is in the algorithm, because you need to estimate both the parameters of the controller, the description of the state, the piecewise affine partition of the state, and then the mode sequence. I will not enter into the details. You can model the same system as before. So the DC controlled motor as a system that switches between two different states. One when I have gravity that is opposed to me, and one when I have the gravity that is according to the motion of the system. And what we end up with is a performance that is at least as good as in the LPV case, but more robust to noise, because I have to switch and I don't have to follow a variable that is continuously varying with time. And we can also, of course, increase the performance by adding the secondary loop as an outer loop. Okay, so we can do something more when we introduce some additional tool to nonlinear system, but there are still many open challenges according to what we have seen before. So not all the problems I mentioned have a solution yet. And if you look at this table, you have a summary of all what we have. So you see that most of the results in the literature refer to explicit and LTI control loops. So you have parametric controllers like PID. You have, let's say, formal guarantees in terms of variable stability, so bounded input, bounded output stability. You know how to do input design. But when you move towards optimization-based or implicit controllers or nonlinear and time-varying systems, it becomes a mess. So that there's no unified approach to these controls. And the most interesting open challenges for me are in terms of experiment design. So how should I design the experiment in order to have something informative for control, how to handle the presence of noise, both measurement noise and process noise, and how to provide formal guarantees. And as a final, last but not least, we have problems in terms of real-world applications. So most of these studies are just, let's say, on toy examples or just in theory, but there are very few applications. So I will say a couple of words very briefly on each of this. So persistence of excitation, why it's important? Well, actually, because we have seen that we have a fundamental assumption that is on the rank of the Hankel matrix in order to have a database representation of the system. Well, actually, this is not the case always. So we can have conditions like this one that I will not comment in detail that are less restrictive than the conditions that we need for system identification. So one data set might be good for control even if it's not good for system identification. How to deal with noise in predictive control? Well, the most effective techniques come from the machine learning world, so they're based on regularization, PCA or dynamic mode decomposition, and these show the, let's say, the best performance. And here you can see a very, let's say, brief comparison with what you get with the model-based approach and the data-driven approach. Here you probably don't see it very well, but this is the data-driven approach is the second one, and the first one is the Oracle solution, so the solution that knows perfectly the system dynamics, and all the others are different attempts using models taken from the data. So using data directly for control can be worthwhile. And you also have problems in terms of convergence with N. So if you increase the data set, the dimension of the data set, it's true that an indirect approach, so an approach based on the model, can converge faster, but it may also incur an asymptotic bias due to process noise, and any problem that you have encounter in modeling, of course, has an impact on control performance. How to do formal guarantees? So there are tools to estimate system properties, like, for example, input strict passivity of a system that are still, let's say, ongoing research. But indeed, we need to provide certificates and quality certificates and properties together with the controller. We cannot just say, okay, this works, and I mean, any customer wouldn't be happy with that. And as I said, last but not least, applications. So real-world applications suggested us a lot of interesting insight into the theory and suggested different directions of research. For example, this was a case study in robotics where we had an implicit force control approach. So in this case, it seems that data-driven control is useless because we know very well what is the model of the robot. And so one could wonder, okay, why should I use a data-driven controller here? Well, in implicit force control, you can combine the advantages of model-based control and data-driven control, because you could use a model-based controller for motion control of the robot and a data-driven controller to control the interaction between the robot and the environment. For example, if you change the material, if the robot is working with wood instead of iron, of course you would have a different interaction in terms of stiffness or description, or let's say of the mechanical interaction. You can do this by modeling, you know, the friction coefficient and everything, or you can do it data-driven. So you run an experiment with a certain material, you have the controller for the whole system, okay? But there's no need to re-implement everything, the controller also for the motion control of the robot. Another thing that was suggested by applications is how to calibrate the controller, so how to formulate the specifications. For example, in case of the MPC, this was a torque vectoring problem. You have an over-actuated problem. You don't know exactly how to formulate it. You want to control the side slip angle of a vehicle. You want to control the torque at the wheels, many different things. So how to formulate well the specifications, you don't know. You can do it data-driven, in a data-driven way by, let's say, importing something coming from the AutoML world, so the automated machine learning world for hyperparameter optimization. So to conclude, learning controls directly from data is worth a try, in my experience, because it's time efficient. You don't need, let's say, much expertise in terms of knowledge of the plant. And in some situations, you can also provide a better performance than the model-based case. But in practice, this is not the case. So when you go to real-world application, you just have preliminary attempts, let's say, I would say, fast prototyping. Well, this is how data-driven tools are used, and then you usually go to trial and errors or model-based approaches for fine-tuning. So we really would like to make it as a long-term goal, a valid alternative to model-based design when the level of uncertainty is high. Okay, and the last remark is that there has been little interaction with the reinforcement learning world, even if the two words, the two fields share a lot of interest in similar applications and similar techniques, also from a mathematical point of view. So another, let's say, long-term goal could be to combine the pros of one word and the other word in order to have a really powerful tool for solving real-world problems. So I thank you a lot for your attention, and if you have questions, I'm here.
Will you send us the presentation afterwards?
Yeah, sure. Yes, please.
Thank you so much for the presentation. I have two questions in respect to data selection. So all your methods based on data. So my question is, how do we decide what is the input and output of data? So for example, since the control autonomous vehicle, they usually can control the go ahead and goes braking or steering. This is usually the calculation from your freedom of the vehicle. But if we say electronic vehicle, we can also control directly the motor rotation and outcome. So in this case, in the data that you create there, which kind of definition we can read the issues. And also in the output side, so how many tasks that we can set up as our outputs? So just to the position control, or that we also want the vehicle to be more stable, so satisfy the passengers inside the vehicle? Yeah, that's my first question.
Yeah, well, that's a very good question. Actually, it's as you also formulated the question, it's an optimization problem. So the best way to design an experiment would be to solve an optimization problem. The problem is that it is a sort of nested trick, because in order to design the best experiment, you would have to know the system dynamics, because you should know which kind of dynamics you have to excite, but you don't know it a priori. So you can do it in two different ways. So one is to iterate. So you start with an experiment, then you have, let's say, different experiment for testing and validation, and you see if your design was satisfactory. Then you could stop there. Otherwise, you have to iterate, because you're seeing that you're not addressing all the dynamics of your interest, or you're not exciting enough. In the linear time invariant case, you have some theoretical conditions that can tell you, okay, this data set is equivalent to the full knowledge of the system dynamics. But this is true only for the linear time invariant case. For example, the rank condition in the matrix tell you, okay, if this matrix is full rank, then you're done. You know that that signal is enough for your purpose. But in a nonlinear case, if you have, for example, additional constraints like the one that you mentioned, you know that you cannot exceed this, or you can just accelerate and brake, then of course you have to iterate. Let's say the standard practice is that you run an experiment that is explorative enough of all your operating regions. So suppose that you want to design an ABS or a braking control system. Well, you want to populate or to fill your data set with all the maneuvers that can be of your interest, so that you can validate along different maneuvers with different drivers, for example. And that provides a sort of extensive empirical evaluation of your final control.
You mentioned that full rank matrix. So I'm thinking that in case of robotics application, which I'm working on the robotics program. So if you have a redundant robot like a 7-dog manipulator, you're controlling the T position, which is 6-dog. So actually there's a mismatch between the application space and the task space. In this case,
well, the robot is not a linear system, so that wouldn't hold anyway.
Okay. And my second question is about how do you say your data is covering enough all the cases?
Yeah, that's the question I always ask myself. There's no full answer to that. It's very application dependent.
Does that mean that all those situations that you haven't tested, so you collect data, will be considered as noise data set?
Well, that's the problem, because I mean, you start with the, let's say, you start with a data-driven setting, so you know nothing about your system. This is our standing assumption. So all what you have is the data. So if you have complete freedom, you run some experiments, but since you don't have prior knowledge, there is no way you can guarantee that that's a full expression of your system dynamics. There couldn't be any theorem that says that. It's just, let's say, something that you know based on your past experience. So you're not using your past experience in order to write down the equations, but you're using your past experience to elaborate which kind of experiments could be explorative enough. So you cannot get rid of the human operator in that sense. That's my impression. Thank you.
Okay, so good afternoon. I would like to thank Professor Gatti for this opportunity to share with you part of my PhD research. And so today we talk about an approach for vehicle dynamics control, the twin-in-the-loop approach. We see an application to active braking. So let's start by seeing what active braking is, since maybe some of you are not familiar with that. So what is the problem in active braking? So the idea is that we want to maximize the braking performance by regulating the wheel slip. So if you look at the plot on the left, you see that we have the optimal braking, the best braking force for a certain value of slip. So this value is not 0, it's not 1. We have a sweet spot, which is something around 0.1, 0.2, depending on the terrain you are driving into. So we want to regulate the slip. If you don't do that, you might have lockage of the wheel, like in the picture at the center, and in worst cases, accidents like the one on the right. Okay, so you want to avoid that. We want to design an active braking controller. This is an high-level scheme of the controller. So the commercial name is ABS. Probably you know it. So if you start from the left, we see that we have the driver pressing the pedal, requesting eventually the activation of the controller. Then the controller takes as input a certain slip reference for each wheel, applies a certain braking torque to the vehicle, takes the measured wheel slip from the vehicle, and closes the feedback loop. So this is the high-level idea. Now, if we zoom in just a few details, at each wheel we can write down the single corner model, which is just an approximation of the balance of forces acting. So we have like the braking force, the inertial force, the friction force. And we can define mathematically the slip as the relative difference between the speed of the vehicle and the speed of the wheel. Now, intuitively, if you look at the arrows, if we have that the vehicle speed is 100%, we are braking, so the wheel speed is smaller, and it's 80%, then the slip is the remaining 20%. So we want to control this value, we want to maintain it around the sweet spot that depends on the terrain, but it's approximately 0.1, 0.2, so 20%. Now, this is the high-level control scheme. Now, how do we design an ABS? So a couple of remarks. I just showed you that the ABS acts on the vehicle. Well, that is true, but we cannot directly test on the vehicle, so we need models. We need very faithful models of our vehicle for safety reasons. So we have to start from models, and so let's go and look at the typical design process for any vehicle dynamic controller like the ABS. So we abstract a little bit. So we consider a generic controller. We want to design this controller, so we take a simplified model of the process we want to control, like the single corner one. So we take the controller, we calibrate it, we test it. We have a certain cost metric which depends on the input and on the output of the model. Now we take our controller and we test it on another model, which is a digital twin, and it is the best available model we have of our plant. So we want this digital twin to be the perfect replica of the system, so we expect some parameters tuning because, of course, the digital twin models other phenomena. It has some nonlinearities, so it's a very faithful model. In general, so the cost metric we get for the digital twin is kind of worse than for the simple model. This is because it's harder to control a more complex model. So the last step, eventually we go to the vehicle. So we take the controller, we calibrated it on the best model we have, we test it on the vehicle. So we expect on the vehicle the same behavior that we have on the digital twin, because the digital twin is the best model. So that's what we expect. For the same reason, the cost metric we get on the vehicle should be the same as for the digital twin. Okay, so this is the system process. Now let's apply it to the active braking case. So we start by taking a controller. So we take a state-of-the-art controller. So we take a model predictive control. It was published last year, so a very recent solution. What is a model predictive controller? Well, it's some controller which is based on an internal model of the process we want to control. At each step, we take this model and we optimize the control action in order to get a certain performance metric we want to optimize. So in practice, we have the predictive model, the optimizer, and an optimization problem, which is made of one cost function, which in this case is quadratic, and some constraints on the states, on the inputs of the system. So we apply all of this at each step, and we control the vehicle. Now, let's test this on the digital twin. So we take the digital twin. So in this figure, you see in the upper part, the front left wheel slip, the lower one, the rear left wheel slip. You see that the tracking performance of the FPC is very good. We are able to smoothly track the reference. Note that we are working on a model which is very, very complex, but it's a model that we perfectly know. So we know the parameters of the model, we built this model, and so we can perfectly tune the controller. Also, we don't have noise in the measurements because we are working in an ideal world. So this is what we get on digital twin. Now let's go to the vehicle. What is the vehicle? So in this project, we did not have the chance to test on a vehicle, so we built our vehicle by introducing some model differences in the digital twin. So we have a new digital twin with modified mass distribution, modified tire rod friction. We also mimic the presence of a sensor by adding some noise in the measurements, some realistic noise, and this is what we get. So the MPC almost fails at controlling the slip, so it's able to somewhat track it, but it does that in a much worse way. So what? So the MPC is not particularly robust to noisy measurements and model uncertainty. Of course, we have some ways to deal with that. Now, two very common ways used by practitioners are, first one, filter the measurements. So you take the measurements, you filter them. Of course, you can do that, but this introduces lag in your closed-loop system, and that is very bad for the stability. So if possible, you would like to avoid that. The second thing you could do is recalibrate the controller. Now, usually this is what you do. You can do it very simply. If the controller is a PID, you just have 2 or 3 parameters. The MPC has many parameters. Some of them are not intuitive to tune, so it's a long and very expensive procedure. The more complex the controller is. So what can we do? So let's go back to our flow. The idea is that we have an high fidelity model of the plant. So we have this high fidelity model. We are just using it to test the controller, but can we use it to actually simplify the controller implementation? So one idea, why don't we take the digital twin and we invert it in order to get the input necessary to have the desired output. So we already know what is the performance that we want to get. So we require the performance of the digital twin and we get the necessary input. This seems very nice. It's actually a state-of-the-art solution, the internal model control. But the problem is that we cannot use it. Why? Because the digital twin cannot be inverted. So it's not a simple model, it's non linear, but most importantly, it's a black box. So usually it's a commercial product, you can set the parameters, but you cannot access to the equation. So you can just use it to predict the output based on some input. You cannot use it in that way. So we have to find an alternative way to do that. And this is where twin-loop control comes to mind. So it's a novel solution, and we directly embed the digital twin inside the controller. We see how in a moment. And we solve the invertibility problem we just talked about by doing the inversion in a closed loop sense. Now, let's go and look at this. So here we have the twin-in-the-loop control structure. In the upper part, we take the digital twin. We already calibrated the controller on that model. So we control the digital twin. We extract the output we want to get on the vehicle. What is the input necessary to get that output is exactly U tilde. So we are inverting in a sense that we are obtaining at runtime the necessary input by controlling the digital twin. Now, if the digital twin and the vehicle are identical, well, we are able to control in open loop the vehicle by injecting this U tilde on the vehicle. However, we know that this is not true because the twin and the vehicle are always different to some extent. So what do? We take the mismatch between the twin and the vehicle, we compare it, and we feed it back through a compensator. The compensator has the task of handling the model uncertainty and the noise, and it has to be simple. So it has to be much simpler than the original control you see above. Now let's apply this framework to our braking case. Okay, so we take back our MPC, the ABS. Now, in the upper part, we have the digital twin loop. So the MPC is controlling the twin. It's extracting the nominal control action, the expected output we want to get. And then we close the loop on the vehicle by using the proportional integral compensator to guarantee the stability. Note that we already calibrated the MPC. So we don't have to calibrate 11 parameters on the real vehicle, but we just have to tune the 2 parameters of the compensator, which is a proportional integral. So a very, very simple controller. So everything seems very nice, but we still have a problem. What is the problem is that C delta controls what? The residual between the twin and the vehicle, which is unknown by the definition because the digital twin is a black box, and we don't know how the vehicle is different depending on the application. So how do we tune this residual? Take into account that performing a test with this scheme means actually going on the vehicle, accelerating, and then braking. So it's a long procedure, it's expensive. So you want a calibration algorithm to be efficient. But you also want a calibration algorithm to be a black box because you cannot write down in forms of equation this residual. So one possibility that we used is Bayesian optimization. So let's go and see how this applies. So what is Bayesian optimization and how we apply it in this case. So the idea is that Bayesian optimization is an optimization algorithm, but it's also a statistical learning algorithm. So we want to minimize a cost function where we cannot write down the cost function in a mathematical sense, but we can collect some samples of this cost function. So what do? We collect some samples of the loss function and we fit a Gaussian process proxy of the cost function, which is our surrogate. And then when we have enough knowledge of this model, we can directly estimate the optimal the global optimum of the cost function. So this is the idea. How do we apply it? So we take back our braking case. So we want to minimize the slip tracking error, which depends on the controller parameters. So we start off by selecting a random set of parameters. With Bayesian optimization, we evaluate the cost function. So we evaluate this cost function. Then we update our Gaussian process surrogate by using the collected sample. And then we select the next point. How do we select the next point? We select it through the acquisition function, which is a function to be optimized at each step in order to select the point based on some metric. For example, we can use the expected improvement one, which select the point guaranteeing the best expected improvement over the overall surrogate function, based on the knowledge you have, of course. So you iterate for n times, and finally you take the best solution. So this is the idea. Now, in our case, we actually have some uncertainty in the cost function. So the uncertainty might come, for example, from road friction, which changes depending on the scenario. One idea is just, so you can optimize on one single uncertainty scenario because you know that that scenario is the most common one. So you have this kind of situation. You have good performance on that scenario, but bad performance in general. One other idea is that you can optimize on the whole set of uncertainty. You do that by randomizing, so you randomly select some scenarios based on the knowledge you have of the probability distribution underlying the uncertainty, and then you get lower performance over the specific case, but much higher robustness over the overall set of scenarios. Also, you can prove some statistical guarantees of the solution through the log over log bound, which is very nice since you cannot write down any equation about the process. Now, we calibrate the controller. Let's go and test it. So we take back the experiment we saw before. We compare the MPC in purple with the twin the loop in yellow. So as you can notice, at the initial part of the plot, we have the step response. So the ABS is activating. We have a much better step response with the twin the loop. This is thanks to the feed-forward term, which eases the work for the proportional integral controller. Also, in the last part of the experiment, we have a much better tracking at a steady state, so once the transient is on. So we look at the performance, and we can summarize with the take-home message. So what do we learn today? We learned that using a digital twin in a control loop simplifies the end-of-line tuning, but to do that, we need model-free calibration. And we also verified that in this case study, the novel scheme outperforms one state-of-the-art benchmark that we selected. Now, before concluding, just a few details about the twin-the-loop framework. So we are actually working on other things apart from this case study. So for example, we're working on suspension control and autonomous path tracking, which are very classic problems in vehicle dynamics. But we also developed another framework, which is the dual of the controller, and it is the twin-the-loop filter, which features estimation of unknown vehicle states and parameters by directly using the digital twin inside the estimation loop. The idea is that also in this case, especially in this case, you need the model-free calibration to get good performance in your closed-loop correction. So this is the list of people which contributed to the project. We started in 2020, and our industrial partners are Ferrari, car manufacturer, and V-Grade, which is a manufacturer of driving simulators. But this is it. Thank you for your attention. Here we have some references about the twin-the-loop approach, and even my contact. So yeah, that's it. Well, the idea is, yeah, that is the idea. Yeah.
Just for tests?
No. The idea is to use the twin-the-loop in production vehicles. Yeah, we're going in that direction.
And so you sell the car to the client. And then does this twin in the loop become updated? I mean, the firmware, is it updated or is it just as it comes out from the factory?
Okay, so the twin the loop, it's a piece of software. Basically, what we did is that you can online estimate the parameters, the physical parameters of the digital twin. For example, the mass. If the mass of the vehicle increases, you can use some estimation algorithm to adapt to that. But yeah, the idea is that the control algorithm, the estimation algorithm remains the same over time, apart from the parameters that might change over time, of course.
Okay. And also, does this twin in the loop device, I mean control, does it adapt to every driver, or is it generic to all drivers? I mean, because if a driver brakes harder, I don't know, more frequently, does it adapt to that?
Okay. Well, for this particular case study, there is a feature of the ABS. So the ABS has to work for any driver. So once you push the pedal, you activate the ABS and you stop controlling the brake. So you don't have authority anymore. So it does not depend on the driver anymore. So you activate the ABS and then the ABS has to control the vehicle. So the driver just has to keep pushing the pedal, as you teach to you in driving school, until the ABS stops working. For other applications, like your rate tracking, for example, you might calibrate the control in general depending on the driver expectation from the vehicle. But yeah, for this application, it's not necessary to adapt to different drivers.
Okay, and final question, as a car engineer or as an engineer that works with cars, electronic or computer engineer, electrical, once the user, the customer, or the driver drives this car for some time, would it be possible for me to extract this information and improve my model? The information used for the feedback in the loop, would it be possible for me to extract?
I mean, possibly yes, if you have some cloud communication with the vehicle, yeah.
Is that currently
I think so. I mean, I think that Tesla is doing something like that currently, yeah. Sure.
Okay, thank you, Federico.
Thank you.
Simone, see you. As you know, in the hall of the department there is the aperitif, and we can see you in just in a while in the hall.